Hello students. In today's lecture, we study about weak intermolecular forces of attraction. We've learned about ionic bonds, we've learned about covalent bonds. Last part of the chapter में we'll study about metallic bonds, but आज we have something, we have a new type जो अभी तक हमने पढ़ा नहीं है. These are called as weak intermolecular forces. These are divided into two categories. एक को हम बोलते हैं Van der Waals force, the other is called as hydrogen bonding. This is something very new, not done अभी तक. So let's understand what do you mean by hydrogen bond. Now, let's say we have a polar molecule. What do you mean by polar molecule? Polar molecule is, let's say हमारे पास HF और हाइड्रोजन फ्लोराइड, हाइड्रोजन डेल पॉजिटिव चार्ज होता है फ्लोरीन पे, डेल नेगेटिव चार्ज. वाई? बिकॉज फ्लोरीन इज मोर इलेक्ट्रोनेगेटिव देन हाइड्रोजन. तो फ्लोरीन क्या करता है? बिकॉज ऑफ इट्स हाई इलेक्ट्रोनेगेटिविटी, फ्लोरीन विल पुल द इलेक्ट्रॉन पेयर टुवर्ड्स इटसेल्फ. हमने ये डाइपोल मोमेंट में किया है, एज अ रिजल्ट ऑफ विच इट डेवलप्स पोलैरिटी. इसको हम बोलते थे आयनिक कैरेक्टर ऑफ कोवेलेंट बॉन्ड. Now, when we have many such HF molecules that come in close proximity of each other, the positive charge on one hydrogen and the negative charge on one fluorine of the other molecule, there is a force of attraction between the two, and this force of attraction is called as a hydrogen bond. तो ये bond जो बनाए हैं, the bonds that we have made over here, these bonds are called as hydrogen bonds. So hydrogen bonding will occur only when hydrogen is bonded to an electronegative atom, and it's not that to any electronegative atom. To which specific electronegative atom? It should be fluorine or oxygen or nitrogen. It should be bonded to these three electronegative atoms. There are certain exception cases जो हम बाद में पढ़ेंगे, and there is this force of attraction between hydrogen and the electronegative atom. This force of attraction is termed as hydrogen bond. So, for a hydrogen bond formation to take place, you have to have a polar covalent compound. It does not occur in non-polar covalent compounds, or it does not occur in ionic compounds. Now, what do you mean by non-polar? Let's say I have a non-polar molecule, जैसे कि Cl2 or let's say CO2. So Cl2 molecules, let's say I have a Cl2, supposedly let's say this is a Cl2 molecule and let's say this is a Cl2 molecule. Between two Cl2 molecules or between two non-polar molecules, between let's say I have similarly मेरे पास दो CO2 molecules हैं, there is no hydrogen bonding between these two molecules. इनके बीच में there is some other weak intermolecular force of attraction which we will study in the last part of the chapter, last part of the topic. ठीक है? So, what exactly is a hydrogen bond? It is an electrostatic attractive force between hydrogen atom and an electronegative atom. Specifically, which three electronegative atoms? Fluorine, oxygen and nitrogen. It is formed in polar covalent molecules only. It is not formed in non-polar molecules. It is not formed in ionic compounds. Ionic compounds में there will be ionic bond. And if we see the bond strength, hydrogen bonds are very weak. I repeat, they are very weak. If we compare bond strength, तो एक hydrogen bond की bond strength is usually in the range of 10 kilojoules per mole to 40 kilojoules per mole. Koi books mein it is given between 8 and 45, but somewhere in this range. But comparing that with a covalent bond ki bond range is between 200 to 450 kilojoules per mole. So if you really compare, it is a big difference in the bond enthalpy. But यहाँ पे there is a small exception. If I compare the bond strength of a very particular molecule, जिसे हम बोलते हैं KHF₂, potassium difluoride, bifluoride, or you can also have sodium bifluoride. In this you have a very important ion. This ion is called as a bifluoride ion. Now in bifluoride ion, the hydrogen bond is something like this. So you have a fluoride ion and you have HF. We know that there is large electronegativity difference, because of which hydrogen will develop a del positive. Here you have a fluoride ion. So between H and F we have a hydrogen bond over here. And this particular hydrogen bond, the bond enthalpy is around 161.5 kilojoules per mole. So usually where the bond enthalpy for a hydrogen bond is around 10 to 45 kilojoule per mole, in difluoride ion the hydrogen bond is nearly 4 times stronger. Sometimes the difluoride ion is also made like this. ऐसे भी बनाते हैं इसको. So this is a very important exception. And the second thing is, you only have difluoride ion. Such an ion is not possible. So unlike HF₂- or difluoride ion, HCl2- or HBr2- or HI2-, these do not exist. So only a bifluoride ion is possible, the other ions are not. And the reason for that is, for hydrogen bonding to exist, or the strength of hydrogen bond, I repeat, the strength of hydrogen bond is directly proportional to electronegativity of the atom it is directly proportional to, it is inversely proportional to atomic size, and it is directly proportional to the tendency to donate lone pair of electrons. This is very important because this will help us compare the strength of hydrogen bonds. I repeat, the strength of hydrogen bonding is directly proportional to the electronegativity of the atom. It is inversely proportional to the atomic size, and it is directly proportional to the tendency to donate lone pair. If you look at the size over here, Cl, Br and I, the size increases. As the atomic size will increase, the strength of hydrogen bond decreases, and the difference in electronegativity also decreases, and hence a bichloride, a bibromide or a biiodide ion, they do not exist. Okay? Now let's compare the strength of some hydrogen bonds. So for example, I have, let's say, fluorine and hydrogen, HF molecule. This can have a hydrogen bond with F, or I have fluorine and hydrogen. This can have a hydrogen bond with oxygen, and I have fluorine NH, and I can have a hydrogen bond with nitrogen. Or what I'm trying to say is, you have HF molecule, one more HF molecule, between them we are going to have a hydrogen bond. Or I have HF molecule, and let's say I have H2O, water. In between these two I can have a hydrogen bond, and I have HF molecule, and here I have NH3. In between I can have H bond. You can also say that this is a force of attraction between the lone pairs present on these and the electropositive hydrogen atom. Now I want to compare, when these three bonds are formed, which hydrogen bond is the strongest. So an easy way to identify over here is when you compare electronegativity difference. Abhi electronegativity difference, since it is HF, 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 the electronegativity difference over here is the same. I repeat, the electronegativity difference is the same. The second parameter I can check is size. So nitrogen, oxygen, fluorine, as I go from left to right in the periodic table, the atomic size decreases. So if I compare atomic size, what is the atomic size trend? Biggest size will be nitrogen, then oxygen, and then fluorine. So from an atomic size perspective, ये जो first bond है, that seems as the stronger bond. However, the strongest bond over here is between hydrogen and the nitrogen over here. Why? Because the lone pair donation tendency to donate lone pairs is the highest for nitrogen, then oxygen, and then fluorine. So the biggest atomic size is, the strongest is this, then, and then. So the lone pair donation tendency over here decides who's the stronger in forming hydrogen bond. Did you people get that over here? Chalo. Now, types of hydrogen bonds. अच्छा, एक और exception करते हैं before we directly jump on to type. Hydrogen cyanide. So if you look at HCN, HCN should not show hydrogen bond, because hydrogen over here is not bonded to an electronegative atom, because the electronegative atom that it should be bonded to should be either fluorine or oxygen or nitrogen. But hydrogen is bonded to carbon over here, so it should not show, but HCN shows H bonding. I repeat, HCN shows hydrogen bonding. It shows hydrogen bonding something like this. So HC triple bond N. If I look at one more HC triple bond N, ठीक है, ये आप बोल सकते हो del positive. यहाँ पे ये lone pair है. And the reason for that is the carbon over here is sp hybridized. And we know that sp hybridization, because of higher s character, 50% s character, the electronegativity of Cn, or carbon over here, there for that matter, is very high. It is pulling the electrons towards itself, developing a delta positive on hydrogen, and you can say a delta negative on the entire cyanide ion, and that is why it shows hydrogen bonding. So the hydrogen bonding reason in HCl is due to electronegativity of the sp hybridized carbon. In cyanide. ऐसे एक दो और examples we will study in the lecture. Now, next we have types of hydrogen bonds. Now there's two broad category of hydrogen bonds. The first category that we have is called as intermolecular hydrogen bonds. Intermolecular simply means hydrogen bonds between two molecules. And the second that we have is called as intramolecular hydrogen bonds. Intramolecular means hydrogen bonding within the same molecule. So we have intermolecular hydrogen bonds and intramolecular hydrogen bonds. Intermolecular hydrogen bond further divides into two parts. The first one is called as homo intermolecular hydrogen bonds, and the second one is called as hetero homo intermolecular hydrogen bond, and the second one is called as hetero intermolecular hydrogen bonds. What is the difference between homo and hetero? Homo means hydrogen bonds between the same molecule, HF, HF, HF. Hetero means one, let's say, is HF, the other is H2O, or let's say one is ROH, alcohol, the other one is H2O. That is called as homo and hetero intermolecular hydrogen bonds. Now let's understand each one of them. Let's start with the first one, intermolecular H bonding. Intermolecular hydrogen bonds is hydrogen bonds between the same molecule. उसमें first start करते हैं. The first one is homo intermolecular hydrogen bonds. Example हमने already लिख दिया है. A common example that is hydrogen bond between HF, HF, HF molecule. Actually, though we have made this linear, in reality HF molecule is in a zigzag manner. उसका hydrogen bond कुछ zigzag pattern में ऐसा रहता है. It is actually like this. So this is homo intermolecular hydrogen bonds. Remember, hydrogen will be del positive and a delta negative on fluorine. What was the second type? hetero. Chalo. So let's understand what is hetero. It is hydrogen bonding between two different molecules. Two different molecules would be ROH. People, ROH stands for alcohol, and H2O. So a hetero intermolecular hydrogen bond. I repeat, one is alcohol, the other is water. This would be called as hetero intermolecular hydrogen bonding. This is hetero intermolecular hydrogen bond. Any questions still here? Chalo. Next. What is the second classification of hydrogen bonding? Intramolecular. What does intramolecular mean? Hydrogen bonding within the same molecule. So this is intermolecular. The second one that we have is called as intramolecular. Intermolecular hydrogen bonding, I repeat, is molecular bonding, hydrogen bonding between the same molecule. Let's start with different examples over here. The first example that we have is called as ortho-nitrophenol. We'll do more of these examples in organic chem. Look at the first molecule. The structure of ortho-nitrophenol is like this. So this bond here, it is within the same molecule. This is called as intramolecular hydrogen bond and plays a very, very crucial role. We'll understand this when we do what are the effects on different properties that hydrogen bond has. Let's write some more examples. The first example is ortho-nitrophenol. The second example is ortho-fluorophenol. This is phenol molecule at the ortho position. Ortho position is, if I number this as 1, 2, 3, 4, 5 and 6, attachments on the first and second carbon को हम बोलते हैं ortho. O stands for ortho, and the force of attraction between this hydrogen and this fluorine, this is intramolecular hydrogen bond. Next example that we have is called as salicylic acid. The structure of salicylic acid is something like this. And hydrogen bonding is between this particular oxygen and this particular hydrogen. Salicylic acid can also be called as O-hydroxybenzoic acid. Next example for intramolecular, all these examples are very important, आपको सब याद रखने हैं. The next example that we have is called as salicyldehyde. Salicyldehyde is again derived from salicylic acid. This is the intramolecular hydrogen bond. So that was example number 4. Next example that we have is the acid that we have here is called as 2,6 dihydroxy benzoic acid. Now from 2,6 dihydroxy benzoic acid, if I remove H plus, because it's an acid donates H plus, we get something like this. इसको हम बोलते हैं 2,6 dihydroxy benzoate ion, and this has not one but two intramolecular hydrogen bonds. So these are the different examples that you need to remember for hydrogen bonding. ठीक है, एक दो और example है आगे with what are the different effects on physical properties हम उसमें पढ़ेंगे. चलो, now let's understand how does hydrogen bonding affect different physical properties. So the first physical property that we'll study is solubility. Now, alcohol is soluble in water. ठीक है, preference अलग होगा, soda thumbs up, but we know that alcohol is soluble in water. So why is alcohol soluble in water? Because polar molecules are, or polar compounds are soluble in polar compounds. And the reason for that is alcohol forms hydrogen bonds with water. I repeat, polar compounds are soluble in polar compounds. You can get, or you actually get questions like these. Which particular compound will be soluble in which? So all polar compounds are soluble in polar compounds. So for example, water, if I consider water mein, so you have alcohol, you can consider acids. 10th standard mein kya hai? Even ammonia is soluble in water, has high solubility. Then glucose, fructose, etc. So you have a polar compound, it will be soluble in water. Non-polar compounds are insoluble in water. Non-polar compounds such as ketones, ethers, alkanes. These are all non-polar and are insoluble in water. So another point you can simply add is polar compounds soluble in polar solvents and non-polar compounds are insoluble in non-polar. Getting that? In organic we'll study about different types of solvents B. We also have something called as non-polar solvents. So all these non-polar compounds will be soluble in non-polar solvents. Next, अभी हमने just पढ़ा that orthonitrophenol has intramolecular hydrogen bond. So if I consider two molecules, the first one is orthonitrophenol and the next molecule is called as paranitrophenol. Ortho was position number 1 and 2, so this was my orthonitrophenol. Paranitrophenol is position number 1 and 4. Positions 1, 2 ortho, ORTHO, position 1, 4 para. Orthonitrophenol is insoluble in water. Whereas paranitrophenol is soluble in water. I repeat, insoluble in water, soluble in water. What would the reason be? It is insoluble in water since it does not form hydrogen bonds with water. And why do you think paranitrophenol is soluble in water? Because it forms hydrogen bonds with water. Did you get that? It is as simple as that. If it is soluble, forms H bonds with that particular polar solvent. Not only that, orthonitrophenol has a lower boiling point. Paranitrophenol has a higher boiling point. Same reason. However, the reason this time is not hydrogen bonds with water, but hydrogen bonds with itself. If I have two orthonitrophenols coming close to each other, they will form no bonds with each other. They'll have very weak intermolecular force of attraction. You can easily separate them, easily distill it out. Paranitrophenol, no. Two paranitrophenols, they come close to each other. They form intermolecular hydrogen bond, as a result of which separating them is this has a higher, you can say, boiling point. And hence, if we do a certain reaction, हम phenols में ना इसका preparation पढ़ते हैं in class 12. When you treat phenol with nitric acid, you get orthonitrophenol, you get paranitrophenol. Reaction होने के बाद अगर दोनों को separate करना है, you just simply do distillation. आप distillation करो, पहले vapors मिल जाएंगे orthonitrophenol का, you distill it out, you have two separate products. And hence we say that orthonitrophenol and paranitrophenol can be separated using steam distillation. Can be separated using steam distillation. So the first point that you need to remember is solubility. The second point that we have is, थोड़ा सा भी डिस्कस कर ही लिया था, boiling point and melting point. if I consider group 16 elements, can someone give me elements of group 16? Oxygen, sulfur, selenium, tellurium, polonium. Okay? Now, if I consider hydrides of group 16, hydrides of group 16 matlab they're compounds with hydrogen. So, water, then hydrogen sulfide, hydrogen selenide, hydrogen telluride. And if I consider their boiling points, if I follow the general trend says as I go down the group, melting and boiling points should increase. So according to general trend, who should have the highest boiling point? H2TE, then H2SE, then H2S. But the highest boiling point is H2O. Then highest boiling point is H2TE. Then is H2SE, and then we have H2S. That is the trend in boiling point. And it's a very, very important trend. Why? Because of hydrogen bonding, what is the state of H2O? It is at normal room temperature, a liquid. But what is H2S at normal room temperature? It's a gas. As a result of which even life sustains. Had H2O there been no hydrogen bonding, there would have been no water in liquid state at room temperature, and life would have not been possible. Anyways, so H2O ka higher boiling point is because of the phenomena of hydrogen bonding. But higher boiling point of H2TE is not because of hydrogen bonding, it is because of its large size, and large size mein aata hai van der Waals force. What is van der Waals force? Last mein karenge. Not only is this observed in group 16, but this is also observed in group 17 similarly. Same if I write the elements of group 17, क्या क्या है मेरे पास? Fluorine, then chlorine, then bromine and iodine. What will be their corresponding hydrides? HF, HCl, HBr and HI. If I follow the general trend, HI should have had the highest boiling point, but who has the highest boiling point over here? HF. Then उसके बाद कौन आता है? HI, then HBr, then HCl. The reason remains exactly the same. Hydrogen bonding in HF and van der Waals forces in HI. Now I repeat, this is not only affecting boiling point, it is also affecting the acidity. What I mean by acidity is, if I want to arrange them according to their acidic character, which is the most acidic? If I look at the electronegativity, it feels that HF is the most acidic, but the most acidic out of the four is HI, then HBr, then HCl, and the reason is same. HF has, because of that H bond, H plus is not that easily released, and HI bonding itself is very weak, there is no hydrogen bonding B, and hence H plus in an HI will be easily released. Did you people get that? Also remember, I repeat, H2O is a liquid, H2S is a gas. Hydrogen bonding also affects the state of the molecules. Any questions here, anyone? Chalo, next. The next point that we have, people, is viscosity. What do you mean by viscosity? Viscosity decides the flow of any particular solvent. So for example, if I consider water and if I consider honey, which is more viscous, which flows easily? Water. Why doesn't honey flow that easily, or let's say ketchup for that matter? Physics may study more about this, but surface tension, there is a particular flow of different layers in the solvent. So similarly, this viscosity is affected by hydrogen bonding. For example, if I consider methanol, methanol is only one OH containing alcohol. इनको हम बोलते हैं monohydric alcohol. Monohydric means containing only one OH. Now if I consider methanol with two OH containing alcohol, इसका नाम है glycol, ethylene glycol, or this is called as a dihydric alcohol. It's called as dihydric because it contains two OH. I repeat, you can call it glycol or you can call it as ethylene glycol. And when I compare that with 3 OH containing alcohol, trihydric alcohol, this particular trihydric alcohol को हम बोलते हैं, everyone has this at home in your soaps, glycerol. Glycerol is called as a trihydric alcohol. Who will have the most number of hydrogen bonds? Trihydric alcohol, obviously more the number of OH, and hence it has a higher viscosity. Not only that, if I club this with melting and boiling point, who do you think out of the three will have the highest boiling point? Glycerol. Compare that to ethylene glycol and compare to monohydric alcohol. Did you people get that? Yes or no? And the same if I consider different types of amines. Primary amine, secondary amine and tertiary amine. Again something nomenclature अब तक किया नहीं है. We'll study this more in organic. इनको हम बोलते हैं primary amine. This is called as a secondary amine, and so more number of hydrogen bonds in primary amine, lesser in secondary amine and lesser in tertiary amines. More the number of hydrogen bonds, higher will be the boiling point, higher will be the viscosity, and also something called as higher will be, or it also affects something called as basic character. We'll study that when we do basicity of amines. With till properties. Next. This was point number 3. Next we have a very particular molecule. The name of the molecule is called as chloral. Chloral का structure कुछ ऐसा है people. It is called as 2,2,2 trichloroethanol. This is a derivative of ethanol. Now chloral ka when you perform hydrolysis, you get chloral hydrate. And chloral hydrate has intramolecular hydrogen bond. यहाँ पे भी please try to understand this, the intramolecular hydrogen bond is not with fluorine, oxygen or nitrogen. It is between hydrogen and chlorine. So in certain rare cases, जैसे हमने पीछे देखा था एक cyanide का केस था and a case in chloral hydrate that we see intramolecular hydrogen bond. Any questions still here? Chalo, one last point. Can you explain this to me? Why does ice float over water? So between ice and water, which is the denser medium? Water. But shouldn't it be the opposite? The solid form should be more denser than the liquid form. So ice should it float in water or should it sink down? It should sink down. But we know that ice floats over water. And the reason for ice floating over water is, again, it goes back to the same thing, which is hydrogen bonding. In ice, each water molecule has 4 hydrogen bonds. As a result of which it has a tetrahedral structure or tetrahedral cage structure बोलते हैं. I repeat, it has a tetrahedral cage structure, or you can see the structure is very hollow. The moment ice turns to water, the cage structure breaks. As the cage structure breaks, so does the bonds, and it becomes, you can say, more denser. And that is why ice floats over water. Even hydrogen bonding plays a role over here. Did you people get that? Chalo, jaldi jaldi. Okay, we now move towards van der Waals forces. So the first van der Waals force that we are going to study, students, is called as Dipole-Dipole Interaction. Now Dipole-Dipole Interaction is something जो हमने hydrogen bonding में already पढ़ लिया है. Hydrogen bonding is nothing but a interaction between two dipole. For example, let's say मेरे पास I have a dipole just like HF, which will have a del positive and a delta negative, and I have another dipole. So the interaction between two dipoles, this force of attraction between the negative part of this dipole to the positive part is called as dipole-dipole interaction. Dipole-dipole interaction is of two types. एक हम बोलते हैं head tail arrangement, which is this. The other one is called as anti-parallel arrangement, which is like this. This arrangement. This is called as dipole-dipole interaction. Now what we need to understand is, in dipole-dipole interaction, the strength is inversely proportional to the cube of the distance between the dipoles. This is a very important point that you need to remember. Now, the second type of interaction that we have is called as a dipole-induced dipole. Let's try and understand what this means. So we have a dipole. So on one end we have a polar molecule and a non-polar molecule. Let's say some example की तरह, let's say we can take HE, non-polar. Now what happens is, this polar molecule, when it comes closer to the non-polar molecule, it induces polarity. So I repeat, this molecule, polar molecule, when it came close to this non-polar molecule, it induces polarity, which was non-polar first. This becomes induced polar, which means the polar molecule induced polarity into this non-polar molecule. And now the interaction between the two, this interaction will be called as dipole, which induced polarity into this non-dipole. The force of attraction here is inversely proportional to the 6th power of the distance between the two, which means the strength is actually very weak, but it does exist. How do we confirm that? It is because of the hydrates of noble gases. It is due to the formation of hydrates of noble gas. However, helium does not form this, but we have observed this in argon, we have observed this in krypton and in xenon. This is the second type of interaction. Next we have instantaneous dipole induced dipole. अब what this means is, हमने first time देखा था two polar molecules coming close to each other. Second case we observed one was a polar, the other was a non-polar. In the third case we have two non-polar molecules coming close to each other. I repeat, दोनों non-polar है. Now what happens is, due to, let's say, movement of electrons here and there, for a very small instant, one of the molecule develops a polarity. So I repeat, this was a non-polar, but it induced a polar. So it became an instantaneous dipole, which then develops, or which that induces polarity into the other molecule. This force of attraction between the two is called as instantaneous dipole induced dipole. How do we confirm this? We confirm this because of the formation of liquid these molecules. You know that H2 is a gas, but you can still have liquid H2. You have liquid F2. You have liquid O2. The reason for formation of this is this interaction which gets developed. Okay? Now, you can also see liquid helium. It has the lowest boiling point in the entire periodic table. It's around 4 Kelvin. थोड़ा कुछ extra trivially, you can go home and check on YouTube how liquid helium behaves or what kind of behavior it has. And the last one that we have is ion-dipole interaction. Now this is very important to understand what is ion-dipole interaction. Now let's say people, we take NaCl, we dip NaCl, we put NaCl in water, NaCl dissolves. But we've never asked the question, why does it dissolve or what happens when it dissolves? We know that it will get converted into Na plus and Cl minus the moment you put that in water. Na plus ion, water mein what happens people? It gets surrounded by which molecule? H2O molecule. This is an ion. We know that H2O is a polar molecule, so it's a dipole. Now the attraction between this ion and this dipole is called as ion-dipole interaction. We've studied this in the form of hydrated radii. हमने hydration energy, lattice energy में इसको पढ़ा है. Similarly, what happens with Cl minus? Cl minus also gets surrounded by H2O. But it's surrounded by hydrogen. This force is called as Ion-Dipole Interaction. And in Ion-Dipole Interaction, the force is inversely proportional to the distance between the interacting ion and dipole. This is, however, student, a non-van der Waals force. But since सारे forces पढ़ रहे हैं एक साथ, we can simply add this. Finally, if I want to compare all the bond strengths, strongest bond will be ionic bond. Then we have covalent bonding. Then we have metallic bond. Then we have hydrogen bonds. And the weakest of the lot will be van der Waals force. Yes, we remember the weakest out of all the van der Waals forces that we learned was London forces. Okay? So this completes all the weak intermolecular forces. The next topic that we will study is molecular orbital theory, and that would complete one half of the chapter.